Welcome, I'm Ryan Holger with TEC. This is a continuation of our prior VAV webinar that we did a couple weeks back. As you know, we never had the chance to get into the terminals. We spent most of our time on the overall design and application. So today we're going to dive into all the terminals, kind of a part two, if you will. Some of you guys indicated you needed PDH hours when you registered. When you do that, I'm going to have quiz questions that pop up. I believe there's 5 of them today, so you need to get 3 of them correct. They are not difficult, but you do have to pay attention in order to get them correct. And then if you get 3 of the 5 correct, we will email you a PDH certificate in a couple weeks. GoToWebinar is going to also send you send everybody some kind of certificate after today, like an automatic thing that they do. And that's fine, no problem there. But that one will not say PDHs on it. We will grade the quizzes and we will send you a PDH certificate separately. We are behind on those because we've done so many webinars lately and had really high attendance on all of them. So we're several hundred certificates behind. So give us a couple weeks and we will get those to everybody. And you should have gotten all the ones through May, I think, at this point. All right, with that, we're going to jump in here. So the first 2 or 3 slides I have here are kind of a recap on VAV systems in general. That way, if any of you were not on the first webinar, you won't be totally lost. If you are watching this in the recorded version, stop what you're doing, go back a couple weeks and watch the VAV one and probably even the VVT one, and then come back and watch this one about air terminals. So in our VAV system, we have some major components. We have the air handler or rooftop in this particular example. We have ductwork, obviously, for the supply, sometimes ductwork on the return, sometimes a return plenum like we have here today. All that's normal stuff we have on lots of systems. And then what we're going to have differently is we have all of these air terminal devices, or you might just call them dampers. Right? Officially, we call them VAV air terminals. So we have all these different dampers for individual zones. The air handling system's job in life is to provide me 55-degree cold air all day long, no matter what. He doesn't do heat. He's just a 55-degree cold air machine. He provides that cold air down into this duct, and then each individual zone has a thermostat controlling its damper to decide if it wants more or less of that cold 55-degree air. So if a zone is hot, it'll open up its damper more and more and more, like we have on this first zone. If a zone starts getting cooler, it'll start shutting its damper off. And it could even shut it all the way down to some minimum ventilation position if it doesn't need any cooling. If the zone needs heat, that's his problem, not the air handler's problem. The zone has to have its own local heating source, meaning a duct heater or a baseboard heater or something like that. The main air handler doesn't do heat. He's a 55-degree cold air machine. Now, there's an exception to that, which we call morning warm-up, where he will provide heat in the morning, just the very beginning of the day, just to kind of temper the space back up, and then he switches into cooling the rest of the day. When I say cooling the rest of the day, I mean every single day, all year long, 365 in the middle of January on polar vortex minus 26-degree day. His job is to make 55-degree air still. These systems are for cooling only buildings. Now there's lots of ways to adapt that, tweak that, bastardize that, however you want to word it. We covered those in the prior webinars on both VVT and VAV webinars, so you can revisit those if you need to. But for right now, we're going to go traditional, 55-degree cold air all day long, no matter what, and no heat during the daytime. The air handling system has to have a way to control the airflow, because as these dampers shut back, the static pressure is going to build up in this duct. So we're going to measure that static pressure, and we're going to use that to slow down the VFD to provide less CFM and less static. There's other ways to handle it, but a VFD is the way we do it with all modern systems. So some of the guidelines that we talked about in the prior week, it's 55-degree air all day, no matter what. I think I've mentioned that a million times. No heat from the air handler during the daytime. He does his morning warm-up, and then that's it. There is sometimes that we might have the air handler heat the air up to 55 degrees, which sounds weird as heck. But if you have really high outside air requirements, we can design the air handler or the rooftop, like I showed in the last drawing, to provide some tempering to get you back up to 55, because you're going to have a bunch of 0-degree air being sucked in. So we can temper it back up to 55. If you're doing that with gas-fired heat on a rooftop, you need to buy the staged gas heat option, which has a stainless steel heat exchanger as well. And then sometimes what we'll do, and we do it all the time now because of code compliance, is that when your building as a whole doesn't need 55-degree air, like all of the zones are backing down because it's kind of chilly outside, so then it gets a little bit chillier inside, we might reset the air from 55 to 57.2 or 58.3 or up to a maximum of 60 just to take the chill off a little bit, so we don't need to run as much reheat in all of the zones. You can only really do that if you have a DDC system though. If you do need heat, that's handled at the zone level. I repeat, the air handler does not provide heat in the daytime. Stop thinking that when you design it. If you need that, it's a different kind of design. We can help you with that. We can lay that out, but the zone layout will be completely different for that type of building. It will not be ducted anywhere remotely the same as a VAV system. So no heat from the air handler. The zone has to take care of the heat. There's numerous ways to do that. The most common is to have a duct heater in the VAV box itself, in the air terminal, but you could also use baseboard. You can have electric heat or hydronic baseboard. You can have electric duct heat or hydronic duct heat. You can even use radiant panels for wall panels, floor panels, or even heated floors. Any of those things can be incorporated. If you're going to heat from overhead, meaning that you're going to provide the heat from the VAV box, all of the ASHRAE standards, including ASHRAE 62.1 and including the ASHRAE handbook, are going to limit you to having the discharge air no more than 15 degrees above the space temperature. So if you have a 75-degree space, which is on the warm side, you cannot have any more than a 90-degree discharge. If you have a 70-degree space, 85 is your maximum discharge. If you have too high of a temperature coming out of overhead diffusers, the heat will hug the ceiling and stratify in the space, which means people have cold feet, 58-degree floors, and 104-degree ceilings, which is ridiculous. So we got to keep that discharge air temperature low. I bring this up because many VAV selections we see from engineering firms will have coils already selected, and when we do the math, they end up being like 120, 130-degree discharge air temperatures, which is never going to work. So we need to back those down and put in either smaller heaters or more airflow, depending on what's needed. The cooling side of the equation on the air handler has to be modulating chilled water or variable speed compression or lots of stages of compression. We talked about that on the last webinar. And then we already talked about the fan having to be a VFD controlled fan. Normally we put the duct static pressure probe 2/3 down the duct. That's the traditional way. The new code requires us to put it, in by new code I mean IECC 2018 specifically, requires us to put the duct probe wherever it has to be, so every single project has a duct static set point of 1.2 inches exactly. And then if we're going to have variable fans, that means we're going to end up with variable outside air intakes, which means we need to have a variable exhaust system, either staged exhaust or variable speed, and we control it based on building pressure. From a zone layout standpoint, typically for VAV systems, you'll have one air handling system covering the entire floor of the building, and sometimes even multiple floors of the building. So the interior zones are cooling only. They never, ever, ever, ever need heating. There's no reason for them to need heating. They have no exposure. All of their perimeter, if you will, is 72-degree spaces on all 6 sides of their cube. So they never need heating. They're cooling only, which is why these are 55-degree cooling only systems. For that reason, you need to keep the interior zones separate from perimeters. So I don't want to have this be one big zone with the south and the interior sharing one VAV box and one thermostat. That would be bad news. So generally speaking, each perimeter needs its own control. The interior needs its own control. And then if you're doing a really good job, the corners will get their own control, because there's sometimes going to be a west zone and sometimes going to be a south zone depending on where the sun is, right? And then the same with all the other corners. On a layout, in this case, a pretty small system, it might look something like this. In this case, here's our rooftop unit. He's providing 55-degree air down this duct. We have 1, 2, 3, 4, 5, 6, 7, 8 boxes on this case. We have one for the west, one for the south, and then we have the corner for that guy and the corner for this guy over here. Then over on the east, it's actually split into 2 zones. I'm not sure why it was like that. Maybe this was a conference room and this was an office. You never want to mix conference rooms with offices. Conference rooms have to have their own thermostat. Copy rooms have to have their own thermostat. Break rooms with refrigerators and coffee pots and all that stuff have to have their own thermostat. Do not mix them with somebody's office. They'll be pissed forever. The interior zone could have been one large zone, but on this job they decided to split it in 2. Maybe it was just easier from a ducting standpoint. But we can have those guys be synced up so they have the same set points all the time so they don't fight each other in that large open area. These 2 guys on the inside, you see they don't have little black boxes on them, but all the perimeter ones do. So all these perimeter zones on this project were designed with either electric reheat or hydronic hot water heat. All the perimeter zones on your building are going to need some kind of supplemental heat. The interior zones are not going to need that. That's going to be one of the major differences here. All right, let's do this first quiz question. And remember, if you need PDHs, you need to answer these quiz questions. You need to get 3 of the 5 correct. So I said this a minimum of 10 times in the past 10 minutes. What is the typical discharge air temperature of a VAV system? Your choices are 50 degrees, 53 degrees, 55, and 57. If you're having any difficulty clicking on the answer, for whatever reason, there's a quirky thing with GoToWebinar. You need to leave the full screen mode, and then you can click on the answer. And then go back to full screen if you want. I don't know why it does that. It's just many people have told me they've had that issue on their computer. So leave the full screen, click on the answer, and away we go. Now, while you guys are answering that, if you guys have any questions you want to type in and ask me, just type them in the chat box. I'll be checking them every few minutes to see what's come up. I'd rather do it as we're kind of going as opposed to waiting till the end. I'd rather just answer them on the fly if we could. So it looks like 85% of you have answered the quiz question, and you're actually doing very well getting it correct. I'm going to close that in 3 seconds, so pick something. And once again, if you need PDHs, you have to pick something. You have to pick something correct, obviously. All right, I'm closing it. And 97% of you got the correct answer, which is 55 degrees is the typical discharge air temperature. All right. Quiz question number 2. Knock these things out early on. When does the heat normally run for a VAV air handler? Normally run for a VAV air handler. Your choices are when the thermostat requests heat, in the morning before the building is occupied, in the winter time, or there is no heat at all. When does it normally run? Looks like most of you guys are getting it correct. We've got a few folks that are off track, but most of you are doing good. 80% of you guys have answered it, so I'm going to close it in 5 seconds. Pick something. 3 seconds. All right, 57% of you got the correct answer. A normal VAV system would have heat in the morning warm-up period. And so answer is B would be the correct answer. All right. All right, so let's get into the air terminals themselves, which was what our main goal was today. So there's lots of types of air terminals, and we'll talk about how they're different from each other and when you might want to use one over the other. A couple of them will hit pretty quick because they're obsolete concepts, but several of them are very common. So we have what we call a single duct VAV box, and the only reason we call it single duct is because we have something called the dual duct. Otherwise, we wouldn't even need to call it that. Most people don't even call it single duct. That's what the manufacturers say. Most people just call it a VAV box or the VAV air terminal or the VAV damper. So if there's no other words mentioned, that's what we're talking about, one of these single duct boxes. The other two common ones that you'll see a lot, well, single duct with reheat are both common, and then parallel fan powered and series fan powered. Those 4 are going to be the most common types that you'll see, but we'll touch on all the types. So these single duct boxes, just a regular traditional box. You can see this guy over here on the left is what he looks like. He's not super sexy. There are some characteristics that we'll point out here. So normally, and by normally I mean just about every single time, every job, there's a round inlet and a rectangular outlet. That is pretty common. And the round inlet is smaller than the rectangular outlet. So when air comes in here at a certain pressure, because the space gets wider, it's going to be leaving here at a lower pressure. One of the jobs of the VAV air terminal is to be a pressure reducing device. Typically, traditionally anyway, upstream of the VAV box was medium pressure ductwork, and downstream was a low pressure ductwork system. So like if you're looking at the SMACNA classes, that would be the typical scenario. Usually on the inlet of the VAV box, we will have 4 to 6 feet of flex duct coming in. We don't want 50 feet of flex duct. That's ridiculous from static pressure resistance standpoint. But usually there'll be a few feet of flex duct coming in, and a lot of that is for sound type reasons. Just like when you have diffusers, we'll have the last couple feet coming off the hard sheet metal, we'll have the last couple feet be flex duct going to the diffuser. That makes it so you can move the diffuser around to get access, and it also helps out with sound. On the left-hand side of this picture, you'll see a big sheet metal box. That is the control enclosure. Sometimes there is no control enclosure, and the control actuator mounts directly onto the VAV box shaft, and there's no enclosure around it. The times that you will need the enclosure are going to be when you have more than just a regular VAV box. So the traditional ones, no enclosure. You just put it on there, you're done with it, you wire over to everything, everything's done. But as soon as you start adding things like heaters or fans, now I'm going to have high voltage power as well as low voltage power, so now I'm going to need an enclosure. On these small single duct boxes, without electric heat, I don't have any high voltage, so I don't need a control enclosure. However, if you're doing something in the city of Chicago proper, you're going to have the enclosure if it's a plenum return, because everything in a plenum has to be in conduit and hence in an enclosure. Interior zones, this is the kind of box you're going to use for almost every project. It's cooling only. There's no reason to have a heater on an interior zone because, like I said, all of his neighbors, left, right, front, back, up, and down, are all warm 70-degree spaces or whatever. So why do I need any heat, right? Unless I have a freakish amount of outside air coming into that zone. Everything in my interior zones is based on the interior loads and has nothing to do with weather. So there is not going to be any heater on here. So that's when you're going to use these single duct boxes. You can add a reheat to them. So if I was to take this box and I was going to use it for a perimeter zone, now I'm going to want to add a reheat to it because that perimeter zone is going to have an exposed wall. So I'm going to need to heat that. Sometimes on interior zones, we might have a little bit of reheat if I'm going to have a lot of outside air. Now, as a designer, don't automatically just default to putting heat on the interior zone, figuring out I'll cover my butt that way, because there's a pretty big price difference from going from a zone with no reheat to one with reheat. And the price difference is not in the form of buying the VAV box, because electric heaters are pretty cheap. The price difference is now you have to run high voltage power over to that guy, and it's labor. And then even more so if you have a hydronic-based system. Chun asked, can we have low pressure at the inlet of the VAV at all? Yes, you can use low pressure category ductwork instead of medium pressure on the upstream side of the VAV boxes. That is possible to do, and it's actually more common now that we're trying to go to lower operating pressures to save fan energy. But each VAV box that you select will have a minimum inlet pressure that is required. And we'll get to that in a little bit. It's a pretty low number, but you'll have some minimum pressure. The VAV box cannot operate unless I have a minimum operating pressure coming to it. Otherwise, it's not going to really do anything meaningful. Sometimes we'll do supply and return tracking systems. By that, I mean there'll be a VAV terminal like this on the supply duct, and there'll be another one on the return duct for that same room. That's not super common, but you'll see it in hospitals and in laboratory environments where they really care about the pressurization control in between zones. Now, ideally, every building would do it that way for every single zone. In fact, this week I was literally talking to someone that had found a residential home zone system that was like that. They had dampers on both the supply and the return for every room. It's a fantastic way to control things and keep things balanced as things change. It's fantastic. But you're buying two of everything and wiring two of everything. So it's not really cost effective. So we don't normally have a return damper unless the space has critical pressure related to control. So think hospital and laboratory before you start putting dampers on the return side of the equation. Oops, what did I click on that wasn't nice? Something yelled at me. What was that? Okay, there we go. There's also retrofit dampers. These are not common at all in any way, but you can use them. So you could have a round-to-round damper. This would be used, so let's say you have a constant volume system, there is no zoning on it whatsoever, and you want to make it into VAV, convert the air handler over, or change the air handler out, add zone dampers, etc., etc. Instead of a round to rectangular, you can get a round to round to make that duct transition easier for you. You could also get a slip-in one if you have a rectangular ductwork. You can get a slip-in one where you cut a slot in the side of the sheet metal and slide this damper in. Neither one of these have the good controllability range that we have with this style. Neither one of these are common. Nobody stocks these like this, so you have to order them special. So they are very, very seldomly used, but they are available if need be. But most of the time, you'll just end up using a regular VAV box and changing your ductwork to accommodate that. But those are existing. You'll see them in the catalogs of the manufacturers. I already mentioned supply return tracking. I should have had that slide in there earlier, I guess. All right, this is another rare one. You're not going to see this very often either. It's a bypass terminal. So for those of you guys that were on the VVT webinar, you realize that we had to have a bypass damper on those type of systems. As zones throttle back, we'd open up a bypass damper to relieve the pressure and solve the problem that way. On VAV, we slow the fan down instead. Well, you used to be able to get these zone dampers that had a built-in bypass. Nobody uses these. They're extremely rare. You may see one once in your career, and that's probably going to be it. But instead of having one central bypass at the air handler, each zone would have a bypass. It's significantly better for control because, like we said, having a bypass near the air handler on the VVT webinar is very difficult to deal with, and you get a lot of leaving air temperature control problems because of it. So having the bypass at each zone is awesome, but nobody was ever doing that or paying to do that. But you could, in fact, have that. I'm actually going to skip those because the chance of you seeing one is like almost nothing. But instead of supplying air to the zone, it'll start deflecting air back into a bypass, which essentially dumps it into the return duct or into the return plenum. And it could be closed all the way and do that as well. All right, dual duct. This is also not a common one, but it's a lot more common than retrofit dampers or bypass dampers. So dual duct means you have a special air handler that simultaneously makes hot air and cold air. It has two different decks. It has two different airflow pathways, right? So there's a return fan coming in and a supply fan going out, and there are two different airflow paths, one for a hot water coil and one for a chilled water coil. And then instead of having my system ducted into one duct, I duct it into two. So I have a cold airflow duct and a hot airflow duct. And then what ends up happening is those two ducts run around the whole entire building. And when they get to the zone level, they go into one of these dual duct boxes, which is a mixing box. It has two inlets and one outlet. And what the system will do is it'll, depending on how much heating and cooling, or rather how much cooling a zone wants, it'll throttle back the cold air damper and open up the warm air damper more. Now, on the positive side, this allows you to do daytime heating if you need to, and you do not have to have any hot water coils in the zone or baseboard or anything like that. I do it all with the air side. But the problem is, from the energy standpoint, I'm taking air that I paid to cool and air that I paid to heat, and then I'm mixing them. Not super smart from an energy standpoint. In fact, the past, I don't even know, 15 years, 10 years, the energy codes all prohibit you doing this. So you're never going to see this on a new install. You only see it on existing systems. Or you might see it on a new install in a real specialty application like a laboratory, but instead of hot duct and cold duct, you'll have a ventilation duct and a cold duct. And that way they can have dedicated ventilation air coming to that zone. So you might see them used in that kind of application for niche laboratory type spaces. But the most of the time you'll see them will be on existing systems. And they'll have two different ducts coming to them and we're mixing it. Now those guys come in two flavors. They come in the standard guy and they come in the premium guy. The standard guy is literally, I'm not even exaggerating, literally two of these single duct boxes that we talked about, this guy exactly right here, two of them strapped to each other. They come off the line as single ducts, and then, I don't know if you can see here, see this little strapping material with 6 screws in it and another one on the bottom. They get strapped side by side. And you bring in your round cold duct, you bring in your round hot duct, and then you have your rectangular combined outlet. That's all it is. It does not do a good job of mixing, so you need to have a long distance after this guy on the discharge side for those two air streams to mix. The premium one is obviously more expensive because it has the word premium in it, right? And this guy is going to be primarily used when I'm trying to do a better job of mixing. So that's the standard one strapped side by side. Premium one, it's all one single design. And inside there's actually baffling devices to force this guy to mix with that guy. So when air comes in on the cold duct and then air comes in on the hot duct, each guy has a baffle on them that causes them to mix together. You can see here there's actually an airflow probe on the inlet, and we'll talk more about those when we talk about controls here in a minute. And then I actually have an airflow probe on the outlet as well. I don't need one on the inlet of the heating, so if I know the inlet here and I know the outlet there, I actually can calculate the inlet of the heating if I really wanted to. So this is just showing some mixing examples, which is just basic math. So just showing you how good it mixes. All right, let's move over. Can you guys still hear me? William said the audio cut out, and I want to know if it's on William's end or my end. So can everybody else hear me? Okay, sounds like everybody else can hear me. So give me 1 second since William can't hear me. I'm going to click on this and type a response to him. Okay. All right, we'll keep on moving, and hopefully William can figure out his audio issue. All right, now we got fan-powered boxes. So like the other types, they come in a standard and in a premium, and obviously the premium costs more. It's better for sound, better for mixing, etc., and we'll talk about that. And then they also come in flavors of series and parallel. So a series fan power box has constant airflow during the occupied hours, constant airflow, and the fan never shuts off. And I'll explain how that works. The parallel box has intermittent airflow on the fan side. It still has airflow always coming into the zone, but the fan in the box turns on and off intermittently, and it's only used for heating purposes. So I'll show you from a diagrammic standpoint how that works, so you understand why they have the names that they have. These are typically used for zones when you need heat, and in many cases on the perimeter zones. So you could put standard single duct boxes on the interior and then put single duct boxes with reheat coils on the perimeter. You could do that, and some designs do that. A more common scenario would be to put single duct boxes on the interior and a fan power box systems on the perimeter. These guys are a little more advantageous than just having the single duct with heat, because these guys can use the plenum air, which hopefully, unless something really bad happened in your building, hopefully is warmer than the 55-degree supplier that they have available to them. It'll use that plenum air, let's just say it's 75 degrees, and it'll mix some of that with the supply air to get me a little bit warmer temperature. Basically, it's going to use the plenum air as my first stage of heat, and then my second stage of heat and third stage of heat and so on can be my hydronic coil or my electric heater. So it tends to be better from an energy standpoint by using that warmer plenum air that I have there for me. So I would encourage you to use fan power boxes on your perimeter zones that need heating on them. Now they cost more than single duct boxes with heat because I gotta buy a fan in there, and they're bigger. They take up more space, and if you do things unintelligently, they could be a sound problem. They will also have some energy concerns from a fan standpoint, but if you do your duct design correctly, which we'll talk about here, your air handler fan can be reduced in size, specifically if you're using series boxes. Your air handler fan will be smaller, and you'll use these little individual fans, and combined, it'll probably be less energy from a fan standpoint. So if you can get the quote-unquote free plenum air as your first stage of heat, and you can at least be net neutral on the fan energy, then these guys can be more energy saving than a single duct box with reheat. Let's look at these guys here. Oops. So here's a series box. So the fan is on the discharge side of the unit, and I'll show you the inside guts in a minute. All of the air for the zone, all of it, every CFM that comes into that zone has to go through that fan. That's why it's in series. When we get to the parallel one in a minute, that won't be true. The parallel fan of the box will be in parallel with the main air handler's airflow, but this guy's going to be in series. So if you look over on the right-hand side here, this round inlet, that's going to be my 55-degree air from my air handler. This rectangular inlet is going to be my plenum inlet, and then my fan's going to be over here on the discharge side. He's going to pull from both of those openings. So the fan, the series fan power box's fan is in series with the main primary airflow fan. That's why we call it series. This fan is going to run continuously during the occupied hours. So when the building goes occupied in the morning, this fan's going to turn on. When the building goes unoccupied at night, that's when he will turn off. That'll be in stark contrast when we talk about parallel boxes here in a minute. Now, when you start up the fan on a series fan power box, the series fan power box has to start before the air handler starts. I'm going to repeat that. The series fan powered box's fan has to turn on first, and then a minute or two later, the air handler is allowed to turn on. If you don't have DDC controls, it's very difficult to coordinate that. Basically, you got to go put a bunch of schedules on your individual zones, if they even have schedulable stats at that point, and tell them to start at, I don't know, 6:45 a.m. and then tell your air handler to start at 6:50 a.m. or something of that nature. If you have DDC controls, those boxes will be in communication with the air handler control, and most of the DDC manufacturers are smart enough to tell all the boxes to turn on first, and then tell the air handler to turn on first, and you, the user, don't have to enter 2 different start times. The reason for this is if you start, these are just typically little squirrel cage blowers, and if you have that fan just sitting there off in the box, and the main air handler turns on, the pressure from the main air handler is going to come down this duct here and into the box, and it's going to push on that little fan wheel, which is going to cause the fan wheel to spin. In many cases, it's going to spin backwards. Then when I apply power to that fan, if I apply power to a squirrel cage style fan that's already turning backwards, it'll continue to run backwards. It's a little quirky electrical fact there. It will not correct itself and start going the right way. It'll continue to run backwards. Now, running backwards, it will move air into the zone. It'll just be a really, really crappy designed backward incline fan instead of a nice forward curve fan, which means you probably only get like 60% of your airflow or something ridiculous like that. So start the series fan first, then turn on the air handling system. It's easy to do that if you have DDC. Now, sound on these guys, there's a school of logic that is, well, you know, if I got a series fan power box, the fan's on all the time, so my occupants will hear it, versus parallel, you know, it'll only be on sometimes and they won't hear it very much. It's actually the opposite logic that holds true. People complain less about sound on the series boxes because they're on all day long and no one hears them turning on and off. It's just a nice little background white noise of air coming out your diffuser, right? They don't hear a click noise of the relay and then hear the fan ramp up and then hear the fan turn off, hear the ductwork expand like you might on another system. This is continuous, so they don't even notice it. It's just a background noise. So I would say in more sound critical applications, if you're choosing between series and series and parallel, series might be the way to go. All right, this is how this guy's looking here from an airflow standpoint. I mentioned he's got to turn his fan on first and then he runs continuously during the daytime. However, I did not mention and should have, if that particular zone needs heat in the middle of the night, instead of turning an air handler on to bring heat, he will just turn this fan on and then he will turn on this guy's electric heat or hot water coil and just heat this one zone. And then when the heating call is over at nighttime for that zone, he'll just shut it back off. So if I'm in a heating only situation, meaning middle of the night, this damper on the left-hand side on the inlet over here ends up shutting, and all of my airflow that goes through this fan gets pulled from the ceiling plenum, which is probably something in the 70 degrees. And then I'll have on the discharge side here, I can have my optional hot water or electric heating coil to heat it up the rest of the way. If I am in the occupied mode and have a heat call, then my damper on the left-hand side will go to the minimum ventilation position that's needed to bring fresh air into the zone, and the rest of the air will pull through the plenum. Look at these little fancy arrows. I thank the guys at Kruger who made these slides that I then borrowed. I'm not a good artist. If I'm in a cooling-only situation, then all the airflow will be going through this guy, and nothing will really be coming through the plenum at all. One thing to be cautious of in terms of sizing these fans, I cannot have the series fan be a smaller CFM than my primary inlet. For example, in this case, if I have 1200 CFM as my design coming in, and I only put a 1000 CFM in fan, well, 200 of that CFM has to go somewhere. It goes back out the plenum opening into the plenum. So then what ends up happening is instead of my plenum having 75-degree air available for any of my zones to use as a first stage of heat, the plenum air gets colder and colder and colder because I'm constantly dumping 55-degree air into it, and now I don't have it usable for heat purposes. So this fan needs to be moving more CFM or the same CFM, either one of those will be fine, more or the same as the primary air inlet. By the way, when we balance these, I'm not an air balancer, but I used to do building automation controls, so I would have to go to every job site with the air balancer. The way we balance these typically is we put a piece of toilet paper on a stick and hold it up here at the inlet and see if it sucks in or if it blows out. And then we keep dialing the fan up or down until we get the toilet paper to hang there evenly. meaning that it's equalized between the two. It's super scientific. I'm going to skip the details of the premium construction type designs. It's just going to mean that there's going to be baffling and insulation in there to absorb some of the sound noise. Because what can happen on these guys, on the left-hand side, the sound noise from this fan could come back out through this inlet on the opening to the plenum. And then if there's a return plenum grill nearby, that sound could make its way down. So by having this side passageway on here with baffling, it dampens that sound down. But obviously it ends up costing more money. All right, so we'll kind of skip over the sexy features of the premium box. Let's look at quiz question number 3. Which fan needs to be started first when the system goes occupied for the day? Your choices are the main air handler fan, the series box fan, or the parallel box fan. All right, so Jessica says there's a damper on the primary inlet, but nothing for the plenum opening. That is correct. There's no damper on the plenum opening, nor is there one needed, because what will end up happening is the fan will be designed to do a certain amount of CFM, say 1,000 CFM, and if my plenum is, or my cooling 55-degree duct is open to 800 CFM, it'll automatically pull the other 200 from the plenum. If my cooling duct is open to 1,000 CFM, it'll pull nothing from the plenum because the pressure will be higher on the inlet side, on the cooling inlet side, so that'll be pushing things along, so it will not pull anything into that plenum opening. I should also mention that sometimes these VAV boxes are ordered with filters on the plenum inlet, which is not a bad idea, but those filters are only for construction time. You put them on there to keep all the drywall dust out of your VAV boxes, because many of these guys in the building are going to want to run the heat to help dry drywall adhesive and paint and stuff like that before the building's occupied, and I don't want all that drywall dust on my fan or my electric heat or anything like that, or my hot water coil. When the building goes occupied, when you're doing the air balancing, those filters come off the inlet plenum, and you do not put new filters back on there. There's not supposed to be a filter on the inlet side of a fan power box in a normal operating system. Now, if you have some filthy, dirty building or whatever, okay, maybe you want to do it. But then again, if you have a filthy, dirty plenum cavity, I'm going to ask, why are you sucking that air in and putting it into the zone to begin with? That's kind of questionable. So the plenum cavity should be relatively clean, right? Don't make the plenum cavity be like your basement crawl space or something weird. It should be relatively clean. You do not need a filter on there when you're operating it. It's only there for construction time. All right, I'm going to close this poll question. And it looks like 91% of you guys got the correct answer, which is the series fan needs to start first. All right, let's look at the parallel boxes. All right, so the parallel boxes work a little bit different. His fan is not going to be at the discharge side of the box, and all of the air is not going to be going through him. His fan is going to be in parallel with the main inlet, and he's only going to be turning on during a heat call. His job is to pull heat out of the plenum, and then if he doesn't need heat in that zone, he shuts off. That's what he does. This is what it's going to look like for him. So in this case, I still have my 55-degree air inlet. I still have my plenum inlet, but instead of the fan being over here on the discharge side, he's over here in parallel with the primary air, and he just pulls plenum air in as my first stage of heat. So if I have a heating call, I'm already going to back my damper down to some minimum ventilation position, because before I get a heating call, I should be having requests for less and less cooling. So this damper on the left is going to already throttle back to whatever his minimum position is. And then if it still gets cold in the space, I'll get a heating call, which will energize this fan, which will suck in my 72, 75-degree plenum air, whatever it is, and mix that with my 55 to give me 60-something degree supplier. And then if I need more heat, second stage will call, and my electric heater or hot water coil will turn on to provide additional heat. Whereas this series box, oops, I'll just use this one. Series box, this fan runs all the time. And if I have a call for heat, first stage of heat would be the electric heater. He's always pulling plenum air in. So unless it's an absolute design day scenario, where this guy's wide open on the damper, the series box is never going to give you 55-degree air in the space. He's always going to give you 57, 58, 60-degree air, because he's always going to have a little bit of plenum air mixed in with the primary air, unless it gets so hot in there that this damper goes wide open. But he's always going to give you the exact same amount of CFM. This will always be 1,000 CFM or whatever that fan size for. So you'll always have constant airflow coming out of the diffusers, which means your diffuser selection becomes less critical. Whereas a regular VAV box, a single duct box, or one of these parallel boxes, diffuser selection, like we talked about a couple weeks ago, is very important because I have to get a VAV diffuser with good throwdown ability, turnback ability, so I have good throw distance data. But it's not critical on a series box because that is a constant volume system downstream of the box, whereas this is always a variable air volume system. So if I'm in the cooling scenario, my fan would be off, and I'd be bringing all my air through my inlet plenum, and that damper could be shutting down more or less as needed. Then when I go into a heating call, this fan's going to turn on and pull air from the plenum instead. And it'll still be bringing a little bit of air from the ventilation side of the equation, so I have some ventilation airflow. And once again, there's going to be a premium box, which is mainly for sound reasons, that has additional baffling and so forth on him. So if I look at these two guys side by side, this is what they look like. Just remember that series means it's in series with the main air handler fan. Parallel means it's in parallel with the main air handler's fan. Series boxes always provide constant volume CFM into the zone. Parallel boxes, just like regular VAV boxes without fans, provide variable air volume into the zone. Always make sure that your primary airflow is less than your zone's fan airflow. Otherwise, you're going to have air coming back out the plenum box or about the plenum inlet. For parallel boxes, the fan is the first stage of heat, and the fan only turns on during a heating call. In each of these series or parallel boxes, you can have Ecm motors or Psc motors. I think you guys are pretty familiar with that technology nowadays anyway, from other walks in life and furnaces and fan coils and all that kind of stuff. Ecm motors, generally speaking, are more efficient, and they typically have more different operating points that we can operate them at in a more easy to control fashion. When I look at these guys, this is a Psc fan curve on the left and Ecm fan curve on the right. And the bottom axis is static pressure on both of these, and the vertical axis is CFM. As the static pressure increases on the Psc fan, I would get less and less airflow. So as things happen in the zone, diffusers get adjusted, ductwork is better or worse than other jobs, whatever it's going to be. There's hot water coils on there, whatever it is, whatever increases my static resistance, external static, will reduce my CFM. These Psc boxes have a little fan controller on them with a potentiometer on it that you can turn with a screwdriver to adjust the CFM for balancing purposes. And that's it. You adjust it one time for balancing purposes to get the CFM that you're specified to have for that project, and then you never touch that thing again. Whereas the Ecm ones, those guys, you're going to not dial in a speed control. You're going to dial in a CFM set point, and they're going to try to get you that CFM no matter what happens with your static. So if coils get dirty, if people adjust diffusers, it's going to keep cranking out the same CFM, just like a variable speed furnace would do at your house. Now, at some point, it's going to fall off because, like in this case, once I get to 0.4 inches of static, I'm now getting the 0.4, or I'm getting my 1,000 CFM at 0.4 inches by operating my fan at full capacity. So now, if I continue to have increased static, I'm already at 100% speed on the fan, so I'm going to lose the CFM at that point. But in its normal design operating range, it'll keep constant CFM. From a controller standpoint, on these Ecm motors, like I said, you can set a CFM set point on them. You can also get ones that have the option of the building automation system controlling the CFM on the fly. That is not common at all, and you probably don't want that. And your building automation guy probably doesn't want that either. Normally, the CFM is set by the air balancer, and then that's it. You don't need to mess with it ever again. There are some unique applications where it needs to be changed continuously during the course of the day. Specifically, if you have an underfloor air distribution system, a UFAD system, you need to control pressure under the floor cavity. So that means something has to do that. That something is going to be a DDC system taking direct control of the fan power box. Other than that, you're probably going to have the kind of controls on the left where you set a CFM and forget it. Ecm motors are more expensive than Psc motors, as you probably know, so it does add to the cost of the box. This slide says $250. It's kind of old. The price gap is a little bit closer now, but it is still more money than a PSC fan. Usually the Ecm motor will save energy compared to the PSC, but that is not always the case. There are examples of when that's not true. This chart here, this is a Kruger fan power box at 2500 CFM, and up the left-hand side is the airflow, and down the bottom is the watts per CFM efficiency. Right, where a 1 would be 1 watt per CFM, so we're at 0.8, 0.6, 0.4. In the pink/purple/fuchsia color is the Psc motor. If I'm up here at 100% airflow, this particular one, let's just say it's operating at 0.5 watts per CFM. Then when I back that guy's airflow off and provide less and less airflow by turning that little speed control on the air balancer, I'm turning the speed control to get the right airflow that I need. I'm backing him down. My efficiency goes down. It gets less efficient. The Ecm motor, in many cases, starts out higher. He's worse efficiency. And this is true on lots of things. Like a VFD is less efficient than a system with no VFD if you're going to operate it at 100%. Once you start turning it down, that's when things get exciting. So ECMs are the same way. This guy's up here at whatever, 0.6 watts per CFM if I'm at full airflow. And when I start turning him down, he gets more efficient. And in this particular example, for this size box with these two fans, the break point was about 80%. If I'm going to operate him at less than 80%, ECM would be the efficiency winner. If I'm going to operate him at more than 80%, PSC would be the efficiency winner. Now, if you recall, we're not changing the CFM on the fly like we would with your furnace at your home, right? Or with a staged air volume rooftop nowadays. This is a one-time set it and forget it. So if you're going to oversize your VAV box and operate it at less than its maximum allowable design airflow, then the ECM is probably going to save you some money. If you're going to select your VAV box right at the max, if the manufacturer says this box can do 2500 CFM, and you're like, good, my job needs 2490, I'm right there at the max. Well, in that particular example, a PSC is probably going to be more efficient for you. But if you use a 2500 CFM box and you only needed 2100 CFM on your job, all right, now the ECM starts making some more sense. Let's see, there's a couple questions that came up. Tim says, architects hate the look of the open return on fan power boxes and open ceilings. Do you recommend anything to cover the opening grills? I would not put grills on them. You can. You just have to do it before you do the air balancing because it's obviously going to affect the air balancing. But I guess from a visual standpoint, a grill would look a lot better than a filter on there. But you could do that. You just have to do it before you air balance. And then Jessica says, a lower efficiency value means that the motor is more efficient. Correct. So in this example, 0.4 watts per CFM is more efficient on a percentage basis than 0.6. So as I go to the left, things get more efficient. So as I throttle the ECM motor back, it gets more efficient when I go to the left. Whereas the PSC motor gets less efficient when I go to the right as I back him down. Some of this debate has been ended because from a code standpoint, in the 2015 and 2018 IECC, series fan power boxes are required by code to have an ECM. Parallel boxes are not because they operate intermittently, but series ones have to have it. So you don't have to even have this debate anymore. You automatically have to put it in if it's a series box. The choice between a series and parallel box is like the age-old debate on VAV systems. Nobody agrees on it. There's no awesome criteria decision on when you should use one over the other. Different parts of the countries have different favorites. Like you might go to Seattle and they might be a series box town, and then you go to New York and they might be a parallel box town or whatever. I'm making up examples. There are some regionalities like that. You can use either one of these, and it's usually designer preference. The main big differences are going to be constant airflow on the series, which means constant sound, and I don't have to worry about my diffuser selection for turn down. Parallel means that I'm running it more for a heating dominated scenario, and I don't need the constant CFM. I can tolerate the higher sound levels. All right, quiz question number 4. Let me get over to that screen. Which terminal's fan runs constantly during occupied hours? The series fan, the parallel fan, neither one of them, or both of them? Which one runs constantly during the occupied hours? Oops. All right, 74% of you guys have answered. So I'm going to close it in 3 seconds. 1 second. And 91% of you got the correct answer, which is the series fan power box runs constantly during the occupied hour time frame. All right, there are numerous insulation lining options available on these VAV boxes. By default, almost every VAV box that you would specify or order is going to come with a 1/2 inch thick fiberglass liner. That's going to be the standard on there. That is mainly there for sound purposes. It would seem logical to me that you would also be lining the inside of your ductwork on these projects. That's not always the case. Sometimes they put a wrapper on the outside of the duct instead, which is fine, but visually it doesn't look as good, as someone pointed out, for the open ceilings. But you're going to get a 1/2 inch fiberglass liner as standard. You could get no liner if you didn't want one. It's going to cost you more. It's a premium to not get the liner, and it's going to be a massive sound penalty. Fiberglass is really good at absorbing sound, which is why if you ever do like a project for like a recording studio or something like that, or you do like a theater, they will have panels on the wall that are made of absorbent material like fiberglass, so the sound can go in there, the sound waves can go in there and kind of get trapped and bounce around and neutralize themselves. So 1/2 inch thick liner is there for condensation purposes and for sound purposes. Every liner option that you pick that is not the 1/2 inch standard one is going to be a sound penalty to you. The possible exception of the 1 inch fiberglass liner. Most of the manufacturers don't even publish a difference on the sound on those two. It's immeasurable. But I'm saying here, maybe about 1 NC difference, maybe, because you have a thicker, but it's not even really a measurable amount. All of the other liner options are going to have a harder surface on them than the fiberglass will, so they're going to reflect sound, which is going to make them be noisier. Having no liner or having a double wall system is going to be the biggest penalty. That's 12 NC. That's an absolute massive sound penalty. It's orders of magnitude larger in sound. There's no reason to get double wall in a VAV box. It does not make any sense whatsoever. There's no advantage to that. The reason people ask for double wall is because they want it to be cleanable on the inside, which usually means it's going to be like some kind of medical facility or a clean room project, and that's why they might ask for double wall or why they might ask for no liner. In those situations, there are other options. You could get a 1/2 inch or 1 inch foil-faced fiberglass, which means it's like this guy over here in the middle on the left, where I can wipe it down. But that still has a sound penalty associated with it because that foil is reflective. Or the best thing you could do would be get the cellular liner, which is like the one on the top left over here, that black pad-looking one. The cellular liner can be completely wetted. You can wash it as much as you want. If we do this class live, I actually have a bowl, like a cereal bowl, made out of that foam, and I will pour water in that and set it on the table for the entire class, and water does not leak through it in any way. It's kind of impressive. So on a normal job, I'd say stick with the 1/2 inch fiberglass liner. And if you have the need for washdown ability, which is not common, but if you did, get the cellular liner and forget about everything in the middle. All it's going to do is cause you more sound penalty than you want. The cellular liner is going to be the quietest of the washable liner options. Oops. On the inlet of the box, there's going to be a flow probe on there. His job is to tell us the CFM. He's actually going to measure static pressure, and we're going to tell him the inlet dimensions of the damper, and he's going to use that to calculate the CFM. And I say he, I mean the VAV box controller that your controls guy is providing on there. Every controls guy is going to need one of these cross flows on here. So the manufacturer of the VAV box provides the cross flow along with a couple feet of pneumatic tubing that go over to the control box, and the controls guy can mount his controller in there, which has the actuator, the heat stage relays, the communications, and a pressure sensor on there. There's two different kinds of pressure probes you can get. Almost every manufacturer uses this cross probe on the top up there. It looks like an X. That's the most common type. Two of the manufacturers use this linear probe. Specifically, that would be Carrier and Kruger. They also offer the option of getting the cross probe if you prefer. The reason they have this linear one on here, even though it looks like it's not, looks like it's made in somebody's garage, really. But it does offer a little bit less pressure drop, which helps out slightly with sound. I wouldn't say it's a big deal. This top one's not loud or anything like that, but because of the dimensions of this, It happens to break up the sound waves better. I'm not an acoustical engineer, but it breaks the sound waves up better and it's a little bit quieter. Either way, there's just two options here of one of these kind of probes you're going to use. These guys are going to be measuring the static pressure and the velocity pressure for us. So specifically, if air is coming in, and looking at the face here, coming in, I thought I had a little arrow on here, maybe I don't. Oh, okay. If air is coming in this way, there's all these little red dots on my drawing, which are little holes on the probe, and that's going to measure velocity pressure because the velocity of the air is going directly into the holes. Then on the back side, now air is going this way. On the back side, where these little green dots are, is going to measure my static pressure for me. Right? So now I have both measurements on there to be used to calculate the total CFM airflow. So if the damper is shut, in this example, I have this installed on a 2-inch duct system. 2 inches of pressure is being provided to all the dampers. If the damper is shut, each one of these probes will end up reading static pressure because there's no velocity of air because the air is not moving. So they're both going to read the 2 inches of static pressure, and hence it's going to tell me there's 0 pressure difference, hence 0 CFM. But then as I start opening that damper up, the velocity pressure will be reading higher than the static pressure that's coming through that guy. And then I can use that to find out the delta P, and that can be used in the calculations to determine the CFM. Right? That just keeps going with more examples. There are several reasons for having these airflow monitoring stations, if you will, on the VAV box inlets. The VAV box is going to be controlled between a minimum and a maximum CFM. That's the main control logic. I did mention a few slides back that there is a minimum operating pressure needed. Usually, as you see on the bottom left of this slide, it's 0.03 inches of pressure is going to be needed at a minimum to operate this thing. There's going to be minimum CFMs for each box. And this is showing you sizes 4 through 16. These are all round inlets. The very bottom of the list has one oddball rectangular inlet, but these are round inlets. Typically, they come in even sizes. 6, 8, 10, and 12 inch are the most common. 6 inches, 8 inches, 10 inches, 12 inches. If you specify anything other than 6, 8, 10, and 12, you should question yourself. For example, if you need a size 4, why do you have a zone that small? What the hell's going on? It's not impossible. You might need it, but it should be questioning yourself. The size 5 box is dumb because a size 5 box is actually a size 4 box with a reducing collar on the inlet shipped to you that way. It is literally that. And a size 7 is a size 5 is a 6-inch box with a reducing collar. A size 7 is an 8-inch box with a reducing collar. I wouldn't buy those anyway. Plus, your sheet metal guy doesn't like odd sizes typically. But in any case, each one of these sizes can have a minimum or maximum CFM that they can handle. If you start getting above that, you're going to be really pressing your luck for both controllability and for sound reasons. So do not go above these maximums. There's also going to be a minimum for each box, as you can see here, 40, 62, 89. That means that how low can I go and still have good controllability? Some manufacturers will publish 2 standard minimums, one for electromechanical and pneumatic controls, and another one that's typically lower for DDC controls, because the DDC controls can typically track and control a little bit better than the pneumatic and electromechanical control options. And then in some cases, there'll be a third one for electric heat as well, because electric heat might need a minimum airflow just to keep the heater online. And the electric heat column will change based on the size of the heater that you're putting in. Let's just stick on the standard one here, for example. So what ends up happening, let's say you needed 500 CFM. Your choices are to pick a 6-inch box or a 7-inch box in that case, right? Or I guess you can even pick an 8, right? If I needed 500 CFM. Now, if I pick the 8 instead of the 6, my box will be quieter. It'll have a larger dimension to it, and it'll have less velocity pressure and hence less sound whistling through it. But my minimum airflow jumps from 89 to 159. If I go below the 159 on the 8-inch box, it becomes difficult to control. Smaller dampers are easier to control in the lower range. Lower range meaning the 0 to 40% damper travel range. It is significantly easier to control if the damper is smaller, because now I'm not operating from 0 to 40, I'm operating in the 0 to 70% range or something like that. Smaller boxes are easier to control. That's true for VAV, it's true for VVT, it's true for balancing dampers, it's true for piping systems with hydronic valves on it. The smaller the valve, the easier it is to control the water flow at the low ranges of operation. Same with airflow in this case. So don't just automatically upsize your box because you want to be a little bit quieter on sound. You have to weigh the decision on what's more important, quietness or the ability to control this without overventilating. If I have to put 159 CFM through my zone and my zone only wants 95 as a minimum, it's going to get more air than it wants, and it's going to be a problem. All these boxes have the ability to add heating systems to them. Both the single duct and the fan power boxes can do that. You can add hot water coils to them. The single duct boxes have choices of 1 through 4 rows. The fan power boxes just have smaller coils because it's already using the fan power box and the plenum warm air as its first stage of heat. You can select them with left or right hand piping connections. By the way, the decision of a left hand or right hand piping connection for a hydronic coil or for electric heater for that matter is a separate decision than the control enclosure. So you can get a left-handed hot water coil and get a right-handed control enclosure and then get it to the job site and say, what the F, man? Usually you want the hydronic connections and the control connections on the same side because it means the opposite side of the box is probably going to get pushed up against the wall. Electric heat options are available in all of the voltages that you would expect. Most common is going to be 208 3-phase and 430 3-phase. You can get single phase for the smaller sizes if needed. If you have a weird 3-phase 3-wire, which does happen in the city of Chicago on occasion for some oddball buildings, that is available. You have to specify that way in advance. It is not easy in any way to convert 480 3-phase 4-wire into 480 3-phase 3-wire. So if you've got a weird 3-phase 3-wire building, you need to tell everybody that up front and tell them 7 or 8 times. Most of these boxes will have 2-stage heaters. The really small heaters might only have single stage. The really big ones might have an option for 3 stages, which costs more money, but you can do it. The more stages, the more better, for sure. You can also get modulating heat. Depending on the manufacturer, you might get an SCR control, which is a variable speed control, not variable speed, but a variable capacity control, or an SSR control, which is also another type of variable capacity control. SCR has been around longer, but the SSR stands for solid state relay. It's probably 15 years at this point that we've had that on VAV boxes, so it's pretty well established. This slide is probably 10 years old, and it said 4 manufacturers offered it. Now it's probably even more. But it's really quiet operation. It can take numerous different types of control inputs to accommodate just about any controls contractor's needs. So it's pretty robust. These are the type of inputs you can use with it. The most commonly selected would be what this particular manufacturer is calling LX4 and LX7. So your DDC controller might put out a 4 to 20 milliamp or 2 to 10 volt signal, and that would be able to go into this LX4 control input and tell it how much heating capacity you want. Or you might not have one of those modulating analog signals, and instead you might have to use 2 of your binary points to create a floating point signal, which is also really common to do, and that guy can handle that. Plus numerous other options in between there that are not as common. From a general control standpoint, you can get these from the manufacturer with no controls, which is very common, and then someone puts controls on in the field. You can order them with pneumatic controls or electromechanical analog controls. You can also get DDC controls. Now, in some cases, like if you order a carrier VAV box, we can provide you carrier DDC controls and do that all as one thing, make it really easy on you. Or other manufacturers, Titus, Kruger, whoever, can also put DDC controls on. What happens in those cases is you send them a drawing of your DDC controls that you want them to mount. They send you their own drawing back. You sign off on it and confirm, yeah, that's the drawing, that's the one I want. You literally sign it and send it back to them. And then you ship them all the controllers. And when they receive the drawing and when they receive the controllers, then they start the lead time clock on however much time they promised you. Putting the DDC controls onto the factory saves a lot of field labor, but it also increases the lead time of the VAV boxes. So you need to plan accordingly. If it's new construction, plan ahead, order the boxes early enough that you can do it this way and save the labor. If it's a tenant finish out, just buy a naked box, no controls, and put your own stuff on the field because you don't have time to deal with this. Like I said, you get left hand or right hand for the controls as well as the hydronic coil. The left hand and right hand is with the air hitting you in the back of the head, meaning you're looking into the round inlet. And that is the control enclosure on the left side or on your right side. We mentioned this last week and earlier today. You have to operate the VAV boxes now to comply with the 2018 code. You have to put the static pressure sensor no longer 2/3 down the duct, and instead you put it wherever it has to go to be exactly 1.2 inches of static pressure set point, or less, I suppose you can do. We have to do static pressure reset like we talked about a couple weeks ago. with DDC controls, you have to do that. If you don't have DDC, you don't have to do this. Because without DDC, it's pretty much impossible. What this thing does is all these boxes talk to each other. And if none of the boxes are open 100%, or maybe say if none of them are open 95% or more, I must be giving you too much air because you're all back down. What I'll do is then change my set point from 1.2 down to 1.1 inches of static. And that means everybody's damper opens up a little bit more. And as long as nobody's opened up all the way, I'll just keep backing that static pressure down and saving fan energy. You also have to do supplier reset controls, and we talked about this previously before, but if you have a 55-degree system, which usually you do, you have to have the ability to reset the supply, not the ability, you have to do the reset between 55 and 60. If the majority of the zones or the average of the zones are saying, hey, we don't want this much cooling, we will start giving you 57.1, 58.3, 59, up to a maximum of 60. You cannot go higher than 60. I guess you could, but you're then going to really lose your ability to control the interior zones, which need year-round cooling. And then lastly, 2018 code was slightly changed from 2015. The summary of all of this language on here is that you have to back your VAV boxes down to their minimum flow on the cooling side before you start engaging the reheat. There's an exception to allow reheat on these systems because they save so much energy in general. Normally, you're not allowed to mix hot air and cold air at any point in time, or you're not allowed to reheat air that's been cooled, including economizer air, by the way. You cannot reheat air that you cooled with your economizer, which is crazy to me, but you can't do that by code. But there's an exception for VAV boxes if you follow these rules. And the two normal ways to do it are you modulate all the way down to the ventilation rate, which I'm showing on number 3 there, or you modulate down to the 20% airflow rate before you energize your heater. All right. Did we have any other questions? Let me pop this last poll thing up, which is the super easy one. All answers are right. It doesn't matter what you answer. This is just your freebie to make up for any of the other ones you got wrong. I don't see any other questions right now on here. Oh, here's one that just came in. So Chun says, also on the same question, can the VAV box or fan power box have high pressure at the inlet and low pressure at the outlet in terms of construction code, operation, maintenance, and make sense at all? Yeah, you can select your VAV box for higher pressures. It's going to start depending on what you're calling high pressure. To me, high pressure is more than 3 inches of static. And you could have a VAV system that has a 3-inch static inlet. You got to select your box for that, obviously. Usually, at least from the energy code standpoint, 3 inches and up is considered high static, which means a lot of things in the code kick in, such as you have to not only seal your ducts, which you have to do on every system, but pressure leak test them, which nobody wants to do. So nobody's designing systems above 3 inches anymore because they want to avoid that like the plague. But 3 inches is typically considered high pressure. 2 to 3 inches is typically a medium pressure, and then below 2 is typically considered low pressure. But yeah, you can have a 3-inch one. You'd be really pushing your luck to say I want to get an 8-inch inlet on my VAV box. Not that it would be impossible, but you'd have to talk to your VAV manufacturer and specifically size it for that, and then also deal with the cross flow and its ability to measure pressures at that range. And the VAV box controller, you'd have to get something special to measure that pressure. He's not going to normally be set up to measure 8 inches of static either. All right, I'm going to close this last little poll question here in 5 seconds. Does anybody else have any other questions they want to type in? All right, well, I thank you guys for joining me. I can't believe that I actually thought at any point in time I was going to include this entire extra hour of information in the last VAV webinar. I totally underestimated how fast these things were going to go. But hopefully that was helpful to you guys. This recording will be posted on our website by the end of the day today. So if you have a coworker that wants to see it, they certainly can. Or if you missed part of it, if you needed the PDHs and you answered 3 of the 5 quiz questions correctly, we will email you a PDH certificate in a couple weeks. You will get a certificate in general automatically emailed to you from GoToWebinar, but that is not the PDH one that you are probably waiting for. All right, thank you guys for your time, and we appreciate it.